Hello viewers, welcome back to the course on matrix computation and its application. So in the previous lecture we have discussed about the two norm of a given matrix. Now in this lecture we will continue with that one. So in the previous lecture we have discussed that for any matrix A we have defined the two norm, and that is equal to the square root of lambda maximum, where lambda is the maximum. So I can define that lambda maximum is the maximum eigenvalue of matrix A transpose A. And we have also seen in the previous lecture that this matrix is positive definite and symmetric matrix. Symmetric matrix, all the eigenvalues will be real, and positive definite means all the eigenvalue will be positive. So that's why we are just taking the square root of this one. So this norm, so this is also called spectral norm, because we know that the spectrum, spectrum is a set of all eigenvalues. So then we are defining the maximum eigenvalue. So this is called the spectral norm. So this two norm is also called spectral norm. Now if A is a symmetric matrix, what is going to happen? Then in this case A transpose A, that will be A into A, and that will be A square. So now if I take the eigenvalue, so eigenvalues of A transpose A is same as eigenvalues of A square, and it means eigenvalues of A and then taking the square. So from here I can say that now if lambda is an eigenvalue of A, which implies lambda square is the eigenvalue of A square. So from here I can define that the spectral norm will become lambda square maximum I can take from here, and then it becomes maximum, this one. So now in this case I can say that the two norm when the matrix A is symmetric is equal to spectral radius of matrix A. So this way we can define the eigenvalue when the given matrix becomes the symmetric matrix. Now after this one, now let us see that if matrix A is non-singular, then I can define the spectral norm or two norm of the A inverse, and that will be equal to 1 over lambda minimum, where lambda minimum is the least, or I can say the minimum value, minimum eigenvalue of, because in this case transpose A. Okay, so I know that eigenvalues of A and its inverse are inversely proportional to each other, then from here I can define that if A is a non-singular matrix, then this is equal to this one. So, I just take that if matrix A is non-singular and symmetric, then I can convert this one into A, because easily then we can define this value. So, now if the matrix is complex, then I can define the same way the 2 norm, and that is equal to lambda maximum under the root, where lambda is the maximum eigenvalue. Maximum eigenvalue means the eigenvalue which has the maximum magnitude of A star A. All other things are same, because A star A means A conjugate transpose A. All other things will be same, and then we can define the 2 norms in the case of complex eigenvalue, complex eigenmatrix or complex matrix. So, this way we can define this value. Now, suppose let us take one example. Suppose I take the matrix A. Now, I take 1 2 minus 1 minus 1 0 3. So, let us I take this matrix, and this is a rectangular matrix 3 cross 1 3 cross 2. Now, I define, suppose it define one norm, so that we already know that it is a maximum of the column. So, I can define from here. So, 1 plus 1 plus 0, 2 plus 1 plus 3, so it is 6. So, everything we already know. Now, I can define its 2 norm. Now, 2 norm I need to find lambda maximum of this one. Now, first I have to define what is A transpose A. So, A transpose A, it means I have to take 1 2 minus 1 0 3. So, this is 2 cross 3, and then I define 1 2 minus 1 0 3. So, it is 3 cross 2. So, now from here I am multiplying here by 1 into minus 1 1. So, it is 2, and then multiplying here. So, it is 2 plus 1 3. Now, this is again 2 plus 1 3, and this is 4 plus 1 5 plus 9 14. So, I got this matrix, that is A transpose A, and of course, this is a symmetric matrix that we can define, check from here. So, this is A transpose A. Now, I want to define its eigenvalues. So, from here I can define A transpose A minus lambda I, that is determinant should be 0. So, from here I get this as 2 minus lambda 3 3 14 minus lambda equal to 0. So, from here it is 2 minus lambda 14 minus lambda minus 9 equal to 0, and that gives me that 28 and minus 2 lambda minus 14 lambda plus lambda square minus 9 equal to 0, and this is lambda square minus 16 lambda, and it will be plus 19 equal to 0. So, I got this value, and now I can find out the lambdas here. So, it is 16 256 minus 76 divided by 2, and now I can define this. So, it will become basically you will get 8 plus minus 3 root 5. So, I got these eigenvalues. So, my lambda 1 is 8 plus 3 root 5 and lambda 2 is 8 minus 3 root 5. So, from here I can say that the 2 norm will be 8 plus 3 root 5 with the maximum value under the root. So, this is my spectral norm of the matrix A. So, here we are taking the eigenvalue of A transpose A, and then we got this value. So, this is my spectral norm of the given matrix. Now, after doing this one, we can have a relation between the eigenvalues and the norm. So, from here I just can make a note. We know that Ax, I am taking any norm, I can write like this one. So, it is a vector norm and matrix norm compatibility condition. Now, for any square matrix A, so that is a square matrix, we can define Ax is equal to lambda x. So, from 1 I can write it is a lambda x is less than equal to and I know that x is never 0, only then we can find the eigenvalues. So, from here this become by the properties of the norm, this become equal to this one, and now x is never 0. So, from here I can cancel out this one, and from here I can say that this condition. So, it says that for a matrix A, if I take its eigenvalues and taking the magnitude, then magnitude of any of the eigenvalues is always less than equal to the norm of that matrix. So, this gives the upper bound for the matrix for the eigenvalues of a given matrix, the magnitude of the given matrix or magnitude of the eigenvalue. So, this is one of the important relation we have discussed. Now, from here, now we are going to define a very important concept, and before that I just write some results. So, in this case we are going to take some results. First one is that one norm is compatible with vector norm 1. Second one is infinity norm is compatible with infinity norm. So, basically in this case we need to show that if I take one norm, then I should be able to write this one. So, that is the compatibility condition, and here also I can write Ax, the infinity norm, that should be equal to infinity norm this one. So, these things we can verify. So, after doing this one more thing we want to discuss is third property, that if you take the 2 norm of a matrix, any matrix A, that is always less than equal to the square root of one norm and multiply into infinity norm, because we have seen that one norm was the biggest one and 2 norm was the in between, and infinity is the smallest one in that case. So, I can say that 2 norm is always satisfy this condition, and this is just, you can see that it is a type of geometric mean of norm 1 and infinity. So, this is also one of the condition we can keep in mind. So, after doing these things, we are going to start a important topic that is called the sensitivity analysis of a system of linear equation. Sensitivity means, suppose I have a system Ax is equal to B. So, this is a system I have. Now, given system there, then x is its solution. I can say it is a true solution. I solve it and I got this value. Now, suppose we perturbed some values in matrix A or B or both, then how the because when we perturb some values in the matrix A or B or in both, then how the solution x is going to change. So, this one we want to see that what is going to happen when we do the small change in the given matrix or on the right hand side. Because why we are doing this one? Because we know that when we have a system Ax is equal to B and we want to solve this system, and this system is maybe very a big system and we want to solve this one. So, we have to take the help of a computer, and in the computer we have different type of error, the round of error or discretization error, that in that case sometimes the small change in the given right hand side vector or in the matrix can lead to this system to a infinite number of solution or no solution. So, that is why we have to check the sensitivity of the given system with respect to the perturbation in the values of A or B. So, this one we just want to study. So, let us take this Ax equal to B, and now suppose I take the concept that case 1 what we are going to do is that let us take some perturbation in B. B means right hand side vector. Now, let B changes to B plus some k, where k is a small perturbation. Small perturbation. Perturbation means small value, and let x will change to x plus some h. Let us see. Now, we want to see that how big the h will be. Okay. So, this one I want to see. Now, a x plus h, I can write from here, this should be equal to b plus k, because when I put b plus k, then I get this solution. So, I call this as 2. Now, from here I can write this as a ax plus ah is equal to b plus k, and here in this case I am considering that a is invertible, because I am considering that this has a solution, that is unique solution it has. So, a is invertible. Now, 2 minus 1, or from 2 and 1 I can write, so I should write it is 3. So, from 1 and 3 I can write from here. So, in this case I can write, because from 3 I subtract 1, then I will get ah is equal to k, this value I am going to get, and from here I can write my h is a inverse k, because it is, I am considering that this is invertible. So, let us take it 4. Now, taking the norm, I can write h, any norm I can take. So, this is equal to a inverse k, I am taking this norm, and this is, I know this is equal to norm of a inverse and norm of k. So, let us write it, equation number 5. Also I know that norm B is equal to Ax norm, and that is less than equal to this one, that is also we know this one. So, from 5 and 6, now from here I can write, so this quantity Ax is bigger than this one. So, from equation 5 and 6, now my h norm is less than this, and this is the bigger one. So, I can write from here my h divided by, suppose I divide by this one, I can write as A inverse k and divided by b, because I am dividing, so this quantity is bigger than b. So, if I divide by this one, then this sign will be there. Now, after doing this one, we can write from here, we can write h and k this one I can write A inverse norm, A norm, and then X B, or maybe I should take this one as, okay, so let's keep it X here and let's keep it K here. Now from here I can write the norm of H divided by norm of X, that is less than equal to A inverse norm, A norm, and this is, I can write K by this one. Now if you see from here, then this is the relative error in B, because we have changed the B from B to B plus K. So it is the relative error in the B with respect to B. So that is a relative error. This is the relative error in X. Now after doing this one, we found a new thing here, because this is the magnification factor. Because suppose this quantity is there, whatever this quantity is there, if this value is very large, then it may happen that this quantity is going to be very large, and then I can say that a small relative change in B leads to very big change in X, if this quantity is very large. But if this quantity is small one, then we can say that a small change in right hand side leads to a small change in the value of the solution. So everything depends upon this factor. So from here I take this factor as A inverse norm into norm A, and I define this as Ka. So this factor is called condition number of matrix A. So this is called the condition number of the matrix A. Only condition is that A should be invertible. Also, I know that A inverse A is equal to I, and from here I can write A inverse A taking the norm both side is equal to I, and norm of I is always 1. Then from here, and this quantity I can take the condition, so 1 is there, so that is always less than norm of A into norm. I am writing here this condition, this one. So from here I can say, and this is what is the condition number. So I can say from here that the condition number of the matrix A is always greater than or equal to 1. So now if this quantity is becoming equal to 1, so now if this is equal to 1, then small change will in this case will lead to the small change in here, because if it is 1, then even the small change here, the small change in X will be smaller than the change in here. So in that case the system will be a condition. So now from here I see that the condition number of the matrix is always greater than or equal to 1. So from here I can say that if small change in B leads to small change in the solution X, implies that system is well conditioned, and in that case the condition number of the matrix is small. is small, and if small change in B implies big change in X, so we say that the system is ill conditioned, and this is possible when the condition number of the matrix A is large. So, large means when the condition number of the matrix is close to 1, then it is well conditioned, otherwise it is ill conditioned, because the small and the large, they are relative terms. So, when this is close to 1, then it is called the condition number is good enough, and if it is a very big number, then it is going to be called as a ill conditioned matrix, or it is going to have a large condition number of the given matrix. So, this way we can discuss about the condition number of a given matrix. Now, once I get this value condition number, so from here now we can write the relative change. So, relative change is here. So, relative change in X is always less than equal to condition number of the matrix A, and then this is the relative change has happened in B. So, this is one of the term we are going to use. So, that is my equation number 7. So, everything depends on the condition number. Now, from here, so this is the case 1 we have taken. Now, I am defining the case 2. So, let there be a perturbation in the given matrix A. So, let us take the perturbation in the matrix A. So, suppose my matrix A changed to A plus E, small perturbation there, and my X changes to again X plus H. Now, I can write from here A plus E, and my solution becomes X plus H, and that is equal to my B. Okay, so, let us write it as equation number 8 in this case. From here I can write this as A plus E X A plus E H is equal to B. Now, also Ax is equal to B. This is the equation number 1 we have taken. So, I can write now from equation 8 and 1. So, I can write from here Ax is equal to B, and B will cancel out. So, from here I can write that I get my Ex plus A plus E, A plus matrix E, and then H is equal to 0. And from here I can write that A plus E H becomes minus of Ex. Now, my matrix, I am considering that A is invertible and A plus E is also invertible. So, A plus E is invertible because only then we are able to find the solution. So, solution exists there. So, I can write my H as A plus E inverse into minus E x, and this one I can write as minus. So, from here I write like this one. So, I just take the A common from here. So, I can write here I plus A inverse E into E x, and this can be written as minus. Now, taking the inverse sign, so I can write here as I plus A inverse E x. I can write like this one. Now, this is equal to H. Now, I am taking norm. I can define the norm of H as, so norm of this one is just I am writing negative sign will disappear. So, this will become I plus A inverse E inverse A inverse E x, and this can be written as less than equal to I plus A inverse E norm A inverse E norm x norm. And now, from here I can define, now let, so I define here that let norm of A inverse E is less than equal to 1. So, let us take this one, because E is a small change in the A. So, we consider that A inverse E is less than 1. So, I can define my H norm is less than equal to A inverse E divided by, this one I can write as I plus A inverse E into x. Now, how we are getting this value? Actually, we are going to make use of this one, that if, maybe I will take the next, that this is what we are going to use. If suppose S is a matrix and norm of S is less than 1 and I plus S is non-singular, then I plus S inverse norm is always less than 1 over 1 minus this one. So, in fact, I am not going to use this concept here, directly we can write. So, I can write from here, then it should be equal to, taking the same way. So, I can write this as a 1 minus A inverse E norm, this one, into x. So, this one we have defined. So, from here I can write that norm of H is less than equal to, I can define E over 1 minus, so from here I can define it like 1 minus A inverse into E and x. Now, it can be written as A inverse, I can write here this, and this one I can write this value, and maybe x I can take on the left hand side. divided by 1 minus A inverse, and I can define this as this one. Now, from here I can define my H norm over X norm can be written as, so this is the condition number. So, I can define the condition number of the matrix, and this is, if you see, that is the relative change in A, 1 minus K A, and this is again the relative change in A. So, in this case also, if the relative change in A, this is small, but the condition number is very large. So, if the condition number is very large, this quantity is going to be very large, and 1 minus 1, this is going to be very small. So, then the whole quantity will become very large. So, it implies that if condition number of the matrix is large, then right hand side is very large. Then we can say that matrix A is ill conditioned, and the system is also ill conditioned. So, everything depends upon about the condition number here, and that is the condition we can define when we take the sensitivity analysis of the given matrix. So, let us take one example and let us see that what is the meaning of this. Suppose I take a matrix A, let us take a simple matrix 2, 3, 2, 3.001. Suppose I take this matrix, and the B right hand side vector I take 5 and 5.001. Let us take this one. Now, Ax is equal to B, which implies that it should be 2x plus suppose 3y is equal to 5, and 2x plus 3.001y is equal to 5.001. Suppose I take this one. Now, if we convert this into the echelon form, so I convert this row echelon form, that gives me 2, 3, 0.001, it becomes like this one, and x, y, then it will be 5, and this is 0.001. And if you solve this condition system, then you will get y is equal to 1 and then x is equal to 1. So, from here we will get a vector 1 1, that is my x solution. Okay. Now, what is going to happen now? I will take the, let us take case 1. So, let us change B, a new B, as, so whatever the B is there, I change, maybe I can define here B plus K as 5, 5. Let us I do this one. So, from here I take my K as 5, 5 minus B, and B is 5 and it is 5.001. So, if you see it, that becomes 0 and minus 0.001. So, this is we have defined. So, K is this one. So, that is the small change we have done on the right hand side B. Now, let us see what is going to happen. So, we are going to solve this condition now. So, I have a Ax is equal to this B 5 5. So, which implies that 2x plus 3y is becoming 5 and 2x plus 3.001y is equal to 5. Now, from here if you see, I can write from echelon form. So, in this case echelon form becomes 2 3 x y, that is 5 here, and then it will be 0 and it will be 0.001, but on the right hand side become 0, and from here I can write that my y will be 0 and the x will be 5 by 2, because it will be 5 by 2 into x, and this is 0. So, that is the my new solution, and from here I get the new solution, that is 5 by 2 and 0. So, now my new solution is x is equal to 5 by 2 and y is equal to 0. So, you can see from here that a small change on the right hand side can lead to the change, a big change in the solution. Here it is 1 1 and now it is coming 5 by 2 and 0. So, this is what we got from here. Also, so let us take the another case. Let us take another case. Case 2. Now, I take the matrix A plus E, change the matrix, and let us take this matrix as a 2 3 2 3. This matrix I take. It means that my E will be 2 3 2 3 and minus A. So, it is 2 3 2 3.001. So, that gives me 0 0 0 minus 0, so 0.001. So, this is I have taken. So, it is a very small change in this one. So, my E is this one. Now, I want to see what is going to happen in the solution. Let us see. Now, it is 2x plus 3y is equal to 5, because right hand side okay, and 2x plus 3y is 5.001, because this is my B, the 5.001. So, we have taken this value. Now, from here if you see, if I write this in the echelon form, so you will get 2 3 0 0 x y. I can write this as, so it is 5 and this is 0.001. So, in this case I can say that in the last equation we can say that it is not possible. So, system has no solution, or I can say that inconsistent. The system is inconsistent, there is no solution. So, you can see from here a small change in the given matrix leads to the no solution of the given system. So, from here by these things I can conclude that this system is ill conditioned. I have not seen the till now we have not seen what is the condition number, but looking at this behavior I can say that this system is ill conditioned, because very small change you can see in the given matrix leads to the system has no solution, or a very small change in B leads to the very big change in the given solution. So, from here I can conclude that the system is ill conditioned. Now, let us find out the condition number of this matrix. So, let us see what is going to happen for this matrix, or I can call it condition number of a given matrix. So, this is going to be norm of A inverse and A, where my A is 2, 3 to 3.001. Now, quickly we can find out this value. So, now I can say that my A matrix is this one, and if you see the determinant, so the determinant of this matrix, it will be 0.002, and its inverse, if you find out, the inverse is coming 10 raised to power 3, and this is 1.5005 minus 1.500, and this is minus 1.00, and this is 1.00. So, this is the inverse we have already calculated, and its value is this one. Now, I can find out the condition number. So, I can find out the condition number with any of the matrix norm. So, let us find out the condition number of the matrix A with norm 1. So, I can write as a with norm 1. It means I am taking 1. So, from here if you see, then I can find out the norm 1 of the matrix. So, it is taking the maximum columns. So, it is maximum, so 4 and 6.001. So, its value is 6.001. Now, A inverse 1 norm I am taking. So, its value if we calculate, then it is going to be, the maximum will be 2.5, and here it will be 2.5 multiplied by 3. So, its value is coming 2500. Now, from here if you see the condition number of A in the norm 1, that is going to be 2500 multiplied by 6.001, and that is approximately equal to 15,000. So, you can see that the condition number of the matrix is very, very large. We expect that the condition number of the matrix should be close to 1, but here it is very, very big. So, from here I can say that this matrix A has very large condition number. So, from here we can say that this system is ill conditioned. Now, the same way we can define the condition number in other format also. So, in the computer we have seen that how we can find the condition number of a given matrix. I have seen that the condition number of the matrix A in 2 norm, it was coming this value, and condition number of A in the infinity norm we have seen that this is coming 15,000. So, based on this one, because we know that all norms are equivalent. So, in this case we have seen that the condition number of the matrix is very large, and therefore, I can say that the given system, that is Ax equal to b, is very sensitive to the change, and hence it is very ill conditioned system. So, we will stop here. So, in the lecture today we have discussed about the condition number of the matrix, and we have seen that how the condition number of a matrix is going to be used to study the sensitivity analysis of the given system of equations, that is Ax equal to b. So, in the coming lecture also we are going to discuss based on condition number of a matrix and other concepts. So, thanks for watching. Thanks very much.